Good afternoon, everybody. Close your eyes and envision a future where your application just runs seamlessly, effortlessly adapting to maybe fluctuations in demand without you having to lift a finger. No more server maintenance, no more sleepless nights worrying about scalability. Well, the future's not just a dream. It's actually the reality of serverless computing. Welcome to Best Practices for Serverless Developers. Hope you're well today. It's awesome to have a lovely audience over here. I know there's a simulcast room in some other hotel, so wave to you over there when you're wearing your headphones. And also, this will be available on YouTube afterwards, so if you're watching that, hello into the future on YouTube. And for joining us in spirit, it's awesome for the people who are here in the room as well. Rand's going to be coming up a little bit later, and so the two of us are hoping that we can give you some good serverless best practices. My name's Julian Wood. I'm a developer advocate working within the serverless team here, and I love helping builders to turbocharge how they can build applications in the cloud, and obviously using serverless technologies. And also, I love acting as your voices internally, so we work with the product teams and other engineers and things to make sure that we're building the best products and features, and so you can take your serverless best practices to the next level, and we can make sure that the next things coming out are the things that you really want. So best practices is a hugely broad topic. We're going to cover it in a number of sections, and we're going to be covering a lot in this talk. So that's just a bit of a warning. If you are watching this on YouTube, you do have the advantage of slowing it a bit down. If you're in the room, you're in for a cool ride. There's a lot more info we wanted to give as well. So we've given this resources slide via the QR code. I am going to share it at the end. The slides are also there as well, so you don't have to go mad trying to take photos of all the pictures. And then links to the slides and many more resources at the end. This talk has also been done at previous reInvents as well. It's not the same talk. We're changing it every single year. But if you haven't seen the talk before, the links are in the resources slide, and there are best practices there. We just want to add some new ones this year as well. So the evolution of serverless has actually been, in my opinion, the story of the cloud. And I'd like to say that the cloud was actually born serverless with the launch of services like S3 and SQS far away in 2006. And this was way before you could actually rent a virtual machine with something like EC2. And then we kept adding services, just pay as you go with no infrastructure to manage. But it was really 2014 where serverless really came alive. It was revolutionary with the launch of Lambda. You just get to upload your code to the cloud, and we will securely run it for you. It's highly available and at scale. And ECS then, for managing containers, came out literally at the same year. With the launch of Fargate, you could also now run and manage serverless containers. So happy birthday to Lambda and ECS. Now, we were thinking of starting maybe a group sing-along today to sing happy birthday, but then Rand said, no, Julian, we've got way too many best practices to get through, so you don't want to hear my singing unless... No, bad idea. We'll just carry on. And obviously, now there are also huge amounts of serverless services across all the bunch of services you can see here, from compute and from storage and workflows and many other different integrations and database and analytics, and that's just with AWS. Huge number of partners who also offer serverless solutions so you can use the best tool for the job. And customer adoption, look at all these names over here, of serverless is everywhere in absolutely every industry, everyone. Startups, and you've got enterprises, governments, and everything in between. And serverless is transforming how they build software. Because they know that going serverless helps them to iterate faster, try out those ideas, and get them in front of customers. So one of the things with going serverless in the cloud is that it just gets better all the time without you having to actually do anything. So looking over here, EventBridge has over time dramatically reduced its delivery latency by up to 94%. Now, we actually, funnily enough, had support requests come in going, hang on, I think there's something wrong with my application. Something's broken because my events are being delivered quickly. What's going on? What's broken? And then also, happy customers relieved to know that it wasn't them, but it was just the service getting much better. But this EventBridge change also actually highlights another pattern that becomes more possible. Before the change, event delivery, you can see on the graph here, was actually quite spiky. And then you can see after the change how latency dropped, but also became more predictable, no randomly waiting for events to be delivered. And of course, you've now got built-in metrics to measure how long it takes to process messages with Lambda, with EventBridge. So what if sync and async were actually not far off from a latency perspective? This can change the mindset that asynchronous is only for those slow, sort of non-facing use cases. So consider a mobile app, maybe for a food delivery that wants to get timely updates from the cloud backend. And the app does some synchronous calls to services to get information about an order, and the front end may talk to multiple backends using the front end to back end pattern. And then, well, the There are also going to be a bunch of additional services that do need to communicate updates to the front end. And communicating with these synchronously are therefore going to be blocking calls. And they're going to be expensive if you have to do repetitive polling. And of course, they're going to cause a bad user experience because you're going to be waiting. But it would be great if you were able to asynchronously route status updates from the back end, from the other services to the front end, without the front end having to poll or having these blocking calls. And there are actually two recent integrations with EventBridge and AppSync, so this front end can subscribe to event updates. And one option is asynchronously routing events to AppSync using GraphQL. Now, GraphQL, if you're not sure, is really powerful for aggregating data. Your clients get just the data they need without having to do sort of many round-trip responses back to the different services. And then on the second side, you've actually got the second one is integrating directly with the new AppSync Events API, a new part of AppSync, which allows you to easily deliver events to a simple WebSocket pub sub topic, and you don't need to know anything about GraphQL. It doesn't even use GraphQL. You just send events, and front-end subscribers can get immediate results. And it's easy to set up an AppSync target in the EventBridge console. If you're using the console, it looks like the GraphQL schema, and then you can see the mutation options available in a drop-down list. And then when you're using AppSync events on the right-hand side, just literally a few lines of code lets you to connect subscribers and connect and subscribe to the API, and then the API destinations actually then push those events. So this seemingly innocuous reducing EventBridge latency makes all this connectivity better. Less spinning and opens up a whole set of different use cases. You now have fast, asynchronous, event-driven architectures. How powerful can that be? And the next topic to cover is serviceful serverless, using configuration rather than code, and then using managed services where possible. And we talk a lot about serverless, and certainly know that that's not the best name to talk about it, but people like to talk also about serviceful. People like Patrick Dubois of DevOps fame and AWS serverless hero Ben Kehoe have been talking about this forever. Serviceful means as an application becomes increasingly serverless, it relies more on external services to provide the building blocks of the system. And so instead of having all your application in a large sort of big compute code base, you can rather migrate those components to discrete managed services. Maybe splitting out the APIs to API gateway example, which can then handle your caching, your routing, and your authorization. You get to use the best service for the job to transport and store the messages. And then smaller services means actually taking advantage of native service capabilities and letting AWS handle the undifferentiated heavy lifting. And this all helps you to really scale your application. You get AWS to take care of the hard stuff and provide that resilience which you really need for your application, and also the security, and often it can also lower costs too. And so when applications become more distributed, well, another thing to think about is how you can then use orchestration and choreography as communication models for different parts of your application. And rather than writing your own code, manage this rather as configuration. And in orchestration on the left, a central coordinator manages the interaction and the order in which the services are used. And then with choreography on the right, there's less central control, and events flow between the services and they react. And many applications obviously use both choreography and orchestration for different use cases. And if you can think of orchestration as workflows and choreography as events. And step functions is a great example of a workflow orchestrator, doing that central coordination and then managing everything as a workflow. And then on the right-hand side of EventBridge, a great choreographer when you don't need strict ordering and workflows, and you can just need events to flow seamlessly without a sort of central control. And with these services, there's also really great opportunities to reduce code, and I love this part. And a common pattern that's often used with Lambda was capturing DynamoDB change events. So on the left-hand side, DynamoDB passes the events and then sends them onto another service, an event bus, or maybe another API for downstream processing. But with using native services, we can remove Lambda from the mix and use EventBridge pipes, so you don't have to manage any of the code. And you then configure the pipe to read from DynamoDB and then configure the API destination parameters. And then pipes is just going to automatically send the events to the API and is going to handle retries and authentication for you. You just get to manage the configuration, eliminating the need for any of the security patching or the maintenance. Super helpful. And with step functions, there's even more chances to remove code. And even with recent updates for using JSON-Nata, this even becomes more powerful. The state machine on the left doing quite a bit of logic with Lambda functions, but if you look inside them, they're actually pretty much just invoking other AWS services. So you can optimize a step with direct SDK integrations like this. So you implement the same business logic, but without running and paying for a Lambda function. And obviously, you can mix and match these different approaches, and you have complete control over what your workflow contains. And in many application architectures, there are also ways to introduce workflows. Now, of course, the world is super keen on building all things GenAI, but actually many GenAI applications can use workflows in the same way as your other applications and your other architectures. And the cool thing is you get to say you're doing something with GenAI. So tool use is a part of GenAI, and it's also called function calling. And this is when you register an existing tool that you have with your GenAI agent. And for this example, we're going to call an internal check inventory database to get some updated information. And so this example uses a GenAI model to parse the natural language from the user prompt, which is going to schedule an appointment for a particular car make for some tires at a point in time. And then the GenAI model is going to work out which of your registered tools can give the information and then generate and formats the JSON so you can query your inventory database. And then our good friend step functions can then do the workflow orchestration, register the possible tools, and send the natural language prompt to the LLM, which responds with the correct tool to use and the JSON payload. So your code can then call your check inventory API, and then even another tool to maybe schedule the appointment. And then I can also store the result and emit an event when done, so another service can then react. And this actually becomes a powerful pattern. You get to use step functions within a microservice bounded context and then emit an event when done so another service can react. This is effective microservice communication using both workflows and events together. And if you didn't know, there are actually two different flavors of step functions. There's standard, and the standard workflows can last up for a year and are asynchronous. And express workflows, these are fast and furious. They're built for high throughput, and they can run for a maximum of 5 minutes and can be synchronous. The pricing is also different. Standard workflows are priced per transition, and express workflows are priced by the number of executions and also the memory that is configured. And so express workflows can actually be significantly cheaper. So in this example on the left, 1 million standard workflow executions, $420. Express workflows, this would be $12.77. And it's also half a second faster per run, so certainly a performance boost. So I suggest take a look at your existing state machines and see where you can potentially save a bunch of money and consider using express workflows first. And the better story is you can actually use both together, nesting express workflows within the standard workflows, and you can have long-running standard workflows that then support the callbacks. And then you get to nest the express workflow, and you get that high speed and that high scale, which then returns back to the parent workflow when complete. It's a great way to get the best of both worlds, which is also often really good for your budget. Well, there's often a case where you need to run some custom code. And I'm obviously suggesting not using Lambda when you can, but running serverless functions and containers have some super interesting capabilities as a service, and it's worth understanding. Starting with Lambda, it's an event-driven execution model. You have something that then causes an invoke, and you have a Lambda function with your code that then does something in your code. And today there are, I think, over 140 different services that natively integrate with Lambda, and there are 3 ways that they do that. It's synchronously, which is request-response, often behind an API. Asynchronously, where you don't wait for a response from the function code, you just hand off the event to Lambda, and Lambda does it for you. And then all the stream or poll-based method, which is called an event source mapping, where Lambda runs a managed poller that reads items from things like Kinesis or Kafka or SQS. Now, Lambda's mostly plug and play when it comes to performance, and there's really only one configuration that you can use to fine-tune your performance, and that's memory. And then when you configure memory, you also get a proportional amount of CPU and networking throughput. More memory equals more CPU, and then Lambda allows you to configure a memory anywhere from 128 meg up to 10 gigs of memory. Now, this graph isn't entirely accurate. It's a bit of a stepping function. It's not a straight line. But it shows that as you increase memory, you get more CPU. And at 10 gig of memory, you get up to 6 virtual CPUs. Now, in order to take advantage of this awesome power, your code does need to support the ability to run across several cores. So a single core performance tops out around 1.8 gig of memory. So if your code isn't multi-threaded and you're scaling memory just for more CPU throughput, well, you're not going to see much benefit beyond 1.8 gig, and you'll be paying a premium for the privilege. So think of if you need to be multiple cores. Now, the next thing to talk about is the Lambda execution lifecycle. And I'm going to talk about cold starts, and I promise you more has been written about cold starts than most other topics with AWS. So what is it? Well, this is when Lambda needs to create a new execution environment to run your code. And there's some time where we need to bring up the environment, bring up the runtime, and make it available to you, and also initialize your function. Now, there are two places this happens, actions that we have to take, and places where stuff happens as part of your code. Now, the cool thing to know is the actual purple text, that cold starts impact less than 1% of production invokes. So you have a production workload with any kind of consistent traffic, cold starts is actually pretty low on the tail end of your traffic. But if you are running synchronous-based workloads, you've got an API, you've got consumers on the other end of that cold start may be important to you, and we're going to talk about some strategies to help. Then also on our side, Lambda is a managed service. We take care of a bunch of things under the hood for you, and that's part of the magic what Lambda does. So every now and again, we need to replace an execution environment if a host has failed, or we need to rebalance the fleet or do things like that. And so sometimes you're going to see cold starts based on the work that we need to do. Taking a closer look at the Lambda lifecycle, we can see where cold starts happen, a number of things. We have to create that execution environment, find a pool of resources on a host that we will run your code on. We then need to download your code or your container image, start the runtime, and then we have what is called your function pre-handler code, which is your code for doing initialization. This is where you're going to grab a secret or maybe connect to a database, and then your function is going to be warm and ready and doing an invoke. Now, in a sort of managed runtime world, there's this demarcation line between what you control and what we can control. And essentially, everything up until there, that init time is on us. And the Lambda team spends vast amounts of time, literally shaving off milliseconds, nanoseconds to make this faster, and trying to make everything as efficient as possible. And everything on the other side of the line is kind of things that you can help and do things with. And knowing the Lambda lifecycle also explains how Lambda pricing works from a cost perspective. You only pay for invoke for managed runtimes. And it's based on a millisecond, based on the number of memory of the function and the duration. And then you do actually pay for init when you're using a container image, an OS-only custom runtime, or when the init is longer than 10 seconds. So this is cost-effective to do when there are gaps from work to do. So some best practices here. There's a lot on the slide. I'm not going to go through everything, but this is about handling your pre-initialization code. Don't load it if you don't need to it. People bundling a whole bunch of stuff in your init code, try and avoid that. Try to maybe lazily initialize libraries, so try to think about how you can establish connections. Sometimes you want to establish connections in the init phase, so you can do something like that and then reuse that connection later on in your function. But then also think about how you're actually going to use state in your Lambda function. You're going to generate state in the beginning, and then you're going to maybe keep state for future invokes, which could be super helpful. But also you need to make sure you want to be keeping the right stuff, and you don't want to have the wrong stuff available to a subsequent invoke for maybe a security or privacy concern. And then there's some other kind of things we're going to talk about, provision, concurrency, and snapstart in a bit. These are effectively ways to pre-warm and pre-initialize your execution environment. Now, there are a couple of other variations of the Lambda lifecycle. One is what happens with snapstart. So snapstart was released 2 ago for Java, and also, just jumped on the slide. Ooh, that actually shocked me. Snapstart released 2 years ago for Java, and actually now for Python and .NET. So this is super useful. This allows you to run your initialization code ahead of time, and then when you want to take a snapshot of your pre-initialized code, your function is going to be able to start immediately. And this is super useful if you're using .NET, and you maybe need to do some compilation of your code, or you need to do some, when .NET does its, when .NET first loads up, it's got to do some of that optimization. That is useful. Or if you're using Python as well, maybe you've got LangChain, or you've got DuckDB, these big kind of things, you can start that in your initialization code, and then it's going to be really fast going forward. And so for every invoke that comes in for a function with snapstart, it's going to start from that pre-initialized environment. And there are only a couple of things you need to think about this. If you are going to connect to a database, you need to be able to rehandle a database connection or a network connection, because you've obviously frozen that connection in the image. But beyond that, there's no other tooling you need to use. There's nothing you need to really do. So this is a really easy, codeless way to be able to do your code starts. You just make your configuration change and can make your functions much, much, much faster. And also, look at the bottom. Remember, you do need to target a function version, not $latest for this to work. So if you're not seeing snapstart work, this is one of the things to look at. So the other thing to know is how Lambda scales up. It does a single request at a time, regardless of invoke model. And so all of a sudden, if you start to get some more requests, well, Lambda is not going to need to spin up some more execution environments, and they're going to cause a cold start and going to start processing that event. However, you can see here that at some point, your first environment becomes free. And so when another invoke comes in, the Lambda server's behind the scenes going, aha, I've already got a warm execution environment ready. I'm going to pass the event to that. And then we deliberately keep these execution environments around for a period of time so it doesn't have to run the cold starts. And if there aren't any free environments, well, it's just going to scale up another one, a Lambda function if needed, and you don't need to manage or control this. Lambda just does this all for you. This means you can actually count the concurrency, which is then equal to the number of running execution environments, and you can view concurrency using the CloudWatch metrics for all or individual functions. So then how does concurrency relate to transactions per second? Well, transactions per second plays a role when you're talking to downstream resources. Maybe you're talking to a relational database, or if you've got an API that can only handle a certain amount of capacity. And so it's going to maybe be constrained by the connections it can affect. And so transactions per second is against the concurrency, helps you then figure out how you can configure this. So you can see here, if I've got 10 invocations and they all take a second to run, well, effectively, I've got 10 transactions per second. But if my function invoke was half as long, I can then fit 20 of them in that time period. So I've still got actually 10 concurrency, it's just a shorter duration. And so performance here is a factor of concurrency and the time that your function runs, and this what looks like a combination of transactions per second. So if I have a downstream service that is going to maybe throttle me at 15 transactions per second, I need to factor that in and think about that in terms of concurrency and how long my function runs. And we've got cool things here. We can actually control this. We've got reserved concurrency, and this allows you to set a threshold of the maximum amount of concurrency your function can run. So if you can allow 20 connections to a database or 50 to an API, you can cap Lambda functions to run at that. And there's also some cool other things you can do with treating it like an off switch, just in case you have times when you've got maybe a downstream issue. You can sort of pause Lambda, fix the downstream issue, and then bring up your concurrency and continue. Another concurrency control is provision concurrency, another way to get rid of cold starts, and this is available for all languages. And basically, you just configure this quite easily for a certain value, and what we go and do is pre-run the Lambda initialization, but we don't do the invoke. And so you can see that all initialization is happening based on the number, and then at some time in the future, the invokes are going to come in, but there's no cold start because that's already happened in the past. If an 11th request comes in, well, that's just going to then do an on-demand invoke and have a cold start. And we just manage this all for you behind the scenes. If we need to replace things or execution environments, we will just make sure that you have, in this example, 10 warm environments happening all the time. Two things to be aware of. Please don't pay for provision concurrency you don't use. There is a sort of threshold where it can save you money, but you really don't want to be wasting your money, and you can use a CloudWatch metric to be able to handle that. And then again, also you need to use function version and latest. So if you're not seeing the provision concurrency what you expect, that's something to look at. Now, another thing we talk about when we talk about concurrency is some of the account and scaling quotas and how fast Lambda can scale. So the account concurrency quota is the maximum for all functions within a particular region, and this is shared between all functions, and it defaults at 1,000, but this can be raised even to tens of thousands. It can be a huge amount. And then last year, we actually changed the scaling model for individual functions, so it's much faster and for all functions. You now have a maximum increase in concurrency of 1,000 for every 10 seconds. And essentially, I think this is incredible. It's the fastest way in AWS to get a whole bunch of compute power behind an application, and plenty of sort of cool innovation happening behind the hood, and Lambda just does this for you. So while we're talking about scaling, here's some tips for synchronous scaling. Ran is going to cover async later, but some best practices. Do your load testing in advance. Make sure you know what you expect and that your quotas all handle things. Set your timeouts correctly. API gateway is 29 minutes. No point setting a Lambda function to 15 minutes. When you do retry, because it's sync, don't overload the system. Use backoff or jitter. Don't cause a stampede when you are retrying. And also think about idempotency. When you do retry, expect to handle duplicate requests and make sure you handle those gracefully. So when you're running a service, you don't charge my credit card twice. That's all I'm asking. And also then while you are doing some stream processing, tips over here, so this could be with Kafka or Kinesis, avoid processing messages you don't need, use filtering, it's quicker and it's cheaper. And then Lambda consumes records in order per partition, so make sure your partition key is spread out correctly. You can manage your function resources and make your code efficient to be able to process things more quickly, and larger batches can also help. Kinesis has got some other bells and whistles. You can use parallelization factor and enhanced fan out, and monitoring is your friend to see if your stream processing is keeping up. Lots of information out there on doing stream best practices with Lambda. So the other serverless compute option is using containers, a really popular way to build applications. Take a container image, build it with whatever you need inside, check it works on your laptop, and then push it to the cloud to run. And there's sort of two components over here if you look on the slide. One is ECS, and that is a fully managed control plane. It's serverless. You can run individual containers as tasks, or you can bring them together as services with a service scheduler, and this can be for long-running tasks with health management and ASIO awareness, and maybe you're going to run a website with this. And then Fargate is the cool serverless part, and this is actually the data plane. And this runs the containers. You can also use EC2 with ECS, but Fargate is the serverless option, and AWS just manages the instances for you. And of course, it's going to work a little differently to Lambda, that it's a more traditional way to run an application, where it's not event-driven, but port and sockets. And you get to run applications with whatever you want to do. And if you need to then route traffic to it, you're maybe going to stick a load balancer in front of it. And there's also a separation of duties. AWS is going to handle then the instance management and scaling, as well as the patching and obviously looking after the underlying hosts. And then compared to Lambda, you then get to choose and you take on more of the management. You've got to patch your own code and your operating system, all the libraries in your container. And then you get to manage the load balancing and the ingress and also some of the networking. And of course, with containers, you get to scale these up and down based on various triggers, and you can use auto-scaling with CloudWatch or third-party metrics. Plenty of best practices for ECS and Fargate, which we're also covering in the resources slide. And so also compared to Lambda, the pricing model is then pay for what you provision rather than Lambda's pay for what you use in milliseconds. And so your container is going to start, and you're going to then be charged per second based on the CPU and memory configuration. So this actually means it could be more efficient to run when you have high concurrency. Lambda has single concurrency, and then you can use multi-concurrency with Fargate and potentially get a lower per cost request. So, a whole bunch of things on the slide here for considerations, choosing between the two, not going through everything, but Lambda just manages a lot more for you. If you're happy to work with a Lambda programming model, once you get started, you can iterate quickly. Fargate lets you do whatever you want to do in a container, really flexible, have more control, use the same container tooling that you already use, and it's got multiple concurrency. Fargate can support larger containers, has more resources, multiple network modes, and can also run forever with multi-concurrency. And Lambda, you've got 15 minutes with its powerful event-based integrations. But if you want the easier version, well, think of Fargate as the flexible operation. Long-running, stable, high-volume, high-resource event sources, and then for Lambda for the simpler option for most other event sources. And of course, it isn't either or. You can actually use both, and even in the same application, using our previous friends Event Bridge and step functions, which can also start Fargate tasks. So this application here processes images and videos on the left-hand side. Files get dropped into S3, which triggers an Event Bridge rule, which then starts a step functions workflow, which is a choice state to either choose between an image or a video. Videos may take longer to run, to process, more than 15 minutes. Fargate's going to be a good choice. Step functions calls ECS and schedules a Fargate task to do the video conversion. Once ECS task completes, sends a success token then back to step functions and can carry on. If it's an image, Lambda's going to be really quick and easy to do that, so it's going to spin up an image file. So, over to Ran.
Thank you, Julian. So, hi, everybody. My name is Ran Eisenberg. I'm a principal software architect at CyberArk at the Platform Engineering Division. I'm an AWS serverless hero, and I have a website called runthebuilder.cloud, where I share everything about AWS and serverless in general. So today I want to talk about building production-ready serverless services. I'm going to share my tips and insights for building such services over the last 5 years at CyberArk. So here we have a simple serverless service. We have an SQS queue. We have the Lambda service polling the queue, invoking a Lambda function with a batch of items. And the function iterates the items and inserts them to an S3 bucket. Simple, right? But is it a production-ready service? And the answer is, of course, no, not really, not even close. In order to be a production-ready serverless service, we need to think about the following 5 aspects: resilience, observability, security, governance, and Lambda best practices. Let's start with resilience. Everything fails all the time, the immortal quote by Werner Vogels. And it is true, everything does fail all the time, and we have to think about it when we are designing our services. So let's say that, for instance, in this case, items are not getting written to the S3 bucket. Now, this could happen due to multiple reasons. For example, S3 might be down momentarily, or the more common issue is that we have a bug in our Lambda function code. In this case, the entire batch of items will fail. The Lambda service will retry the Lambda function again. It's going to fail again. It's going to retry it again, and on and on and on, until at some point the retention period of the items is going to expire, and the items will get deleted forever. So not really resilient, right? We have a problem. But we can fix it. We can add a dead letter queue. In this case, after a pre-configured number of failures, the items will actually move to the dead letter queue where they are not going to be retried, at least for now. So some best practices around this pattern. First of all, you should use a batch size of 10 items. This is the maximum size, and it allows the best throughput for the Lambda function. You should set the visibility timeout to at least 6 times of the function timeout. Now, this will allow your Lambda function to actually finish the processing of the batch while taking into consideration Lambda function failures, and Lambda throttles. You should also define the max receive count to at least 5. Again, this is the pre-configured number that after which the failures, the items will move to the dead letter queue. And again, it's a good compromise while taking into consideration the throttles and retries. And lastly, you should set the message retention period to be a long amount of time on the dead letter queue, so items are not going to be expired and deleted. And we're going to refine this number in a few slides again. So now we have a dead letter queue. That's great. The items are just there, so we need to do something about it. So we're going to add the redrive mechanism. And this is essentially an event bridge scheduler that is going to invoke a Lambda function once a day, twice a day, however you want to set it. And the Lambda function is going to call an API and move the items from the dead letter queue to the original SQS queue, where the items are going to be reprocessed again. And hopefully, this time S3 is up, or we fixed our bug in the function, and they will be successfully processed. So some best practices around that. I did mention all the items that will move to the dead letter queue are supposed to be failures that are retriable, like throttling or bugs that we can fix. We don't want to have any infinite redrives. So for instance, if you have an issue like input validation schema where the item fails, you don't want to basically move it to the dead letter queue because it's going to fail again, and again, and again. So you can just log the item, have an error log, and iterate to the next item. Now, this is the refinement of the dead letter queue retention period. It should be longer than the redrive cron job frequency, because obviously, we want our cron job to have items to move from the dead letter queue back to the queue. And lastly, we should think about item potency. Item potency means that since we have multiple retries on the same items, if you have any side effects on your Lambda function, you want them to occur only once. And item potency is a mechanism that ensures that. OK, so we have our redrive, we have our dead letter queue. That's great. Let's deep dive into the Lambda function and see how we can do the batching. So the Lambda function is going to iterate the items, going to process them, and it's going to use the AWS SDK to put the items into the bucket. And it has built-in retries and backup configurations, and we can change them, and we're going to see how. And you should, because sometimes these configurations are just too long and don't make any sense. Another concept is partial failures. And think about when you have a batch of 10 items. One has failed. You don't want to move the entire 10 items to the dead letter queue. You just want to move the one item that has failed. So we're going to see how you can do that. And lastly, we're going to use Power Tools for AWS Lambda. For those who don't know, Power Tools for AWS Lambda is an amazing open source library that has basically a collection of production-ready utilities that you should definitely use. And we're going to see it in action in a second. So we're going to write a Lambda handler, Python variation. And we're going to use the Power Tools batch handler processor. So in line 6, I'm going to define the batch processor. I'm going to set it to a type of SQS. Do you have other types and other options for other than SQS? And then I'm going to set the model for the order SQS record. That's a pydantic model. That's my input validation schema for each of my items. It has a built-in support to do the parsing for you. And then in lines 9 through 14, I'm going to call the batch processing itself. I'm going to pass it the event, the processor, the context, and lastly, the record handler. Now, the record handler is basically my business domain function where I do it's my code that I write, and where it basically inserts the item to the bucket. Now, what part2 is going to do is it's going to iterate all the batch. It's going to do the input validation and call my record handler with the single item. So here you can see the record handler itself. Now, as Julian mentioned, we're going to use minimal imports in line 1. I'm going to import just the client. I'm going to do the global initialization in line 5, because when the Llama is warm, I can keep the connection already up and running to S3 and reduce my latency, my runtime. And lastly, in line 8, we're going to call the put object. And with this definition, it's going to use the default configuration that AWS has, the SDK, for retries and timeouts. And like I've mentioned, you can change them. And we can change them by using the config class from the Boto core library. So here you can see that we can change the number of retries, the maximum number of attempts, the mode, adaptive or standard. And I highly suggest that you check out the documentation to see which makes more sense to you. You can change the read timeout, and you can change the initial connection timeout. In line 14, we pass the custom configuration to the client itself. So here you can see the entire code, but I want to shift the focus to the concept of partial failures. And here you can see in line 11 that I'm using the put object SDK call. Now, if an exception were to occur here, Power Tools would actually catch the exception, mark the item as failed, partially failed, and iterate to the next one. So you're basically getting the partial failures feature out of the box in a very, very transparent manner. Now, like I've mentioned, idempotency is also very important. And let's say that you have other side effects after line 11 that you're gonna use. Now, since this code might have multiple retries, you want to have idempotency. And also, Power Tools, they have idempotency feature built in that you can use. And if you want to learn more about how to use idempotency with Power Tools and CDK, you should check out my blog post in the QR code below. OK, now let's talk about observability, which is another important aspect of production-ready services. And observability is basically the unified language across the organization that allows us to debug a customer request across multiple teams and services. And it's consisted of CloudWatch logs, CloudWatch metrics, X-ray traces, CloudWatch dashboards, and alarms. Let's start with the logging. So some general tips. You should use structured JSON logging, and this allows you to then filter in the CloudWatch console by every field that you want. You should add the correlation ID and customer ID to all of your logs, not just the error logs, because then when you have an error, you can take the correlation ID and the customer ID and see the entire flow of the customer request across multiple services from the beginning up until the error itself. Now, logs, you need to store them, and it can add up, the cost. The cost can add up. So some tips around that are set the default log level to info, use all your logs in debug level, and really think hard about what you want to use as the info level. And the info level needs to, each log that you select as info should really be like a log that really matters, right? It gives you really important information for your use case. Now, lastly, you should set the retention policies on the log groups for 14 days. I think that 14 days is more than enough, but you can change that if you want. Now, CloudWatch metrics and alarms basically tell us the performance of our service and can tell us if there's any looming problem coming on before our customers tell us that we have a problem, which is not great. So some metrics that are relevant to our service is SQS, the number of messages deleted. And if this number is 0, then you know that messages are not getting deleted and we actually have failures going on. For the dead letter queue, approximate number of messages visible. If this number, you should set an alarm. If there's a large number of dead letter of this number in a short time frame, it means that we have had failures and messages actually move to the dead letter queue. Something is wrong. Lastly, you should also set metrics, alarms for any other metrics or other like Lambda throttles or errors, which are exceptions that you didn't catch properly in your code. Any error logs that you know that you wrote that mark specific failures, critical failures in your code. And you should also use custom CloudWatch metrics, which are great for the product team to define any service KPIs and feature adoptions and things like that. X-Ray, AWS X-Ray. So this is a great service to understand the bottlenecks in your service, the entire performance. And this is an actual trace of the service that we're seeing here. You can see the overall function time, the initialization time, and the actual API call to S3. So you can really deep dive into even the record handler function and understand which function takes you more time and fix it and refine it. Lastly, you have the CloudWatch dashboard, which visualizes all the observability elements that we've discussed in one place. And I highly suggest that you create them with infrastructure as code, and you should define two types of dashboards. One is the high-level dashboards, which is great for a firefighter team or the product team to really understand in quick glance whether you have a problem in your service. And the other one is the low-level dashboard, where you can really deep dive into the metrics and see all the logs in your service to really find any more problematic issues. If you want to see more examples of how you can build CloudWatch dashboards with CDK code examples, check out the QR code below. OK, so I've discussed observability. Let's add observability to our Lambda service, to our Lambda handler with Power Tools. So Power Tools get you covered. You have your JSON loggers, you have your connection to X-Ray, and you have your custom CloudWatch metrics all built in. So in lines 7 through 9, we're going to initialize the logger, tracer, and the custom metrics handlers. We're going to set the decorators. And then on our record handler function, in line 10, I can decorate it and say, because I really want to know how much this specific function takes, I'm writing the log in line 12 with the debug low level. And in line 14, I'm adding a custom CloudWatch metric. It's called bucket items, and I added +1. It means how many successfully items I've written to the S3 bucket. So basically, you can see how easy it is with Power Tools to add observability to our Lambda function. OK, so we started with 3 icons. We now have 8 icons, but we're not done yet. Let's talk about security. We're all familiar with the shared responsibility model, where AWS takes care of the security of the cloud. And as the customers, we take care of the security in the cloud, whether it's our business domain logic code or our infrastructure as code configurations. So some tips around that: don't log your PIIs, the private identifiable information of your customers. I think that's pretty simple and straightforward. You should configure secure settings in your infrastructure as code, things like enable encryption, intransit, and also at rest. Most people get just one or the other, but not both. Block public access to private resources, and audit access to your customers' data. So looking back at our service, we have our S3 bucket. Do you think it's really secure and production ready? No, but we can make it. And we can make it secure by blocking the public access, by attaching an access logs bucket, by enabling encryption. We can use either S3 or our customer managed keys, and we can enforce SSL communication. And here I have some CDK code example where we're building this secure bucket. So I have this function, create bucket. It gets as input the access logs bucket and a Boolean, whether it's a production environment or not. In line 10, I enable the encryption. I'm using S3 managed encryption. I'm blocking the public access in line 11. I'm enforcing the SSL in line 13. And I'm attaching the audit logs in line 16. Now, in line 12, I'm setting the removal policy to destroy if it's the dev environment, because I don't care about this bucket. It doesn't have any customer data. But in production, even if for some mistake, reason, whatever, the bucket gets deleted, I want to retain it because it has customer information. So if you want to see the entire code of the entire service, and actually in this specific code, check out the QR code above. Governance. Governance is also very critical. Usually, governance is taken care of by the IT and the DevOps teams in the form of AWS Config, AWS Control Tower, AWS Organizations, SCP, and they recently released RCP. But we should be aware of that, and developers should also be aware of governance. And it usually comes to a fact we're using stack tags. So you should add stack tags for service, microservice, and team. And it's very useful if you have multiple teams deploying to the same AWS account. It really enables you to understand which resource belongs to each team. And if you're using AWS Cost Explorer, you can then filter by those tags and really understand how much each service is costing you, which is very important. You should also use security scanning prior to your deployment. Use tools, open source tools like CDK-NAG or CFN-linked. For once, I use CDK-NAG, which scans the CloudFormation template output during the deployment, and it scans for any misconfigurations and security issues, and it actually fails my deployment if it finds issues. Okay, so we started with 3 icons, and we've ended up with 9 icons, which is quite a lot. And again, like I said, you can check out the entire GitHub repository with the CDK code, CI/CD pipeline, testing, everything is there in the GitHub repository. But my point here is that building a production-ready serverless service is complicated, right? It takes a lot of effort. And for us at CyberArk, when we got one service, we understood that we need to build more. We were building a SaaS, so we had like hundreds of services to build. So we asked ourselves, how do we replicate these principles, the resilience, observability, security, governance, Lambda best practices? How do we replicate all these principles quickly across the organization? Or in other words, what are the best practices for scaling serverless best practices? Now, I know it's a mouthful, but think about it, it does make sense. And the answer is very, very simple. 2 best practices, service blueprints and architectural patterns. Let's start with service blueprints. So serverless service blueprints are actually a GitHub template repository that have a minimal serverless service implementation. It's a good starting point for us developers because it reduces our cognitive load and it allows us to focus on writing the business domain logic. And again, it has all the best practices with the resilience, security, observability, governance, Lambda best practices. For example, at CyberArk, for us, we built a CRUD API blueprint, which is an API gateway, Lambda, and a DynamoDB. And it has all these tools and best practices built in, a CI/CD pipeline, infrastructure as code, and it's fully deployable and testable on the first day. Now, I took the liberty to create a new GitHub open source, awesome AWS serverless blueprints, and it's a collection of community serverless service blueprints. So you have different backend services, different CI/CD pipelines, different infrastructure as code languages, different programming languages. So my action items to you is basically take a look, find your fit. If you can't find your fit, use it as inspiration and create your own. Open source it and open a PR here so I can add your variation. The second best practice is architectural patterns. So let's take a look back at our service. And here I can spot 2 architectural patterns. These 2 patterns are actually, they have 0 business domain logic in them. And I can just cut them out and reuse them in other services. Or in other words, these are reusable black boxes for best practices. They empower governance and security. And developers can use them in the form of CDK constructs or Terraform templates and don't really think about it. And here again, I've gathered some websites that provide you with free architectural patterns. So check them out. OK, so we've discussed our production-ready service. I want to shift the focus back to production-ready Lambda functions and give you some of my tips. We don't have a lot of time, so I'm going to give you only a few. So the first one is when we're starting to build a new service, we have our GitHub repository, and we need to think about the folder structure. So what works for me usually is that I have my service folder, which is the business domain where all the Lambda code resides. I have the tests folder, unit test, integration, end-to-end. Infrastructure, for me, it's CDK. And I think this is a great example of how serverless empowers developers to use the DevOps culture. Because let's say I want to add a new Lambda function, then all I need to do is first add the CDK code in the CDK folder, and then add the business domain logic into the service folder. The second interesting best practice here is to use hexagonal architecture or architectural layers. So you have the handler layer, the logic layer, and the data access layer. The handler layer does the input validation, initializes the globals and configurations, passes the input to the logic layer. The logic layer does the business domain logic part and uses the DAL interface to interact with the concrete database implementation. This is how you should write your Lambda functions. Power tools, I've mentioned them before. We've seen the Python variation, but there are other languages. We have 4 different languages and so many other utilities. You have data extraction, streaming, caching, feature flag, and so many more. So I highly suggest that you check them out because they're super useful. Now, as Julian mentioned, when you increase the memory of your Lambda function, you get more CPU and network bandwidth, but you can also change the CPU architecture to Graviton, which is an ARM-based architecture. And in many cases, you can get similar performance but pay like 40% less. So in order to find the best price to performance ratio, you should use Lambda power tuning. And Lambda power tuning is, again, an open source that spins up a step function that invokes your Lambda function across multiple configurations and generates you this lovely graph where you can see the fastest invocation time and the lowest cost. And then you can choose whatever ratio makes more sense to you. Now, you should also upgrade the runtime. Now, as I mentioned before, there's a shared responsibility. Sometimes when you upgrade your runtime, you get some security features, but sometimes you get also performance improvements. Back to you, Julian.
Thank you, Ran. And actually, this upgrading your runtime is one of the silliest, easiest hacks in all of computer science, is just keep your stuff up to date. Obviously, there's a security impact to this as well, but people don't often think about the performance impact. And when you are being billed by the millisecond, as you are with Lambda, just upgrade your stuff. Makes things faster, can make things more efficient. And yeah, it's just one of the easiest things to keep up to date. And already with Lambda, when Lambda is keeping the operating system up to date, the libraries up to date and everything, if you've got some sort of good testing infrastructure and using Ran's best practices for scaling out your best practices, well, this can all work really together. And you're only looking after your function code. Hopefully, it's a lot easier to upgrade your runtimes. But I do understand that upgrading your runtimes isn't actually always that easy. Even though I'm flippantly saying it is, often that isn't quite the case. So, of course, we can bring on GenAI. And Amazon Q has got code transformation capabilities, and this may be able to help. And I've actually used it and tested it out to transform applications much quicker than manually. And it currently actually works transforming Java 8 to Java 17. And also, we're working on being able to support this with .NET. And what it's going to do, as good GenAI tool is going to do, is going to be able to look at your package dependencies, look at them, look at the frameworks. It's going to be able to look at some deprecated code, and it's going to be able to add some security best practices. And then Q can also run tests to actually validate and upgrade the applications. Now, our people internally, we tried this internally, and an internal team successfully upgraded over 1,000 applications from Java 8 to Java 17, and I think it only took 2 days. It only took days. OK, some of them may have taken longer, some of them may be really quickly, but 10 minutes on average. That's a really good use case to be able to do that, and apparently the longest one took, I think, just less than an hour. So, I mean, heck, anything that can explain code to me, can help me write it, can help me do some unit tests, and can help me do some CloudFormation, well, that's going to be certainly useful. So I suggest it's worth trying at least Amazon Q for that kind of thing. But of course, many other coding assistants as well are also super helpful when building your serverless applications. So many people ask me then, what's next? What's coming on for serverless? Are we all done? No, not at all. We can see the room is full here today at reInvent. All the sessions for serverless are completely full because the road ahead is bright. There's so many things still to happen. And the way we're going to do this is we are going to continually build well-architected best practices just natively into the services. We're going to work hard on improving the developer experience. We've had a bunch of recent releases that have come out. There's a brand new Lambda console. It looks like Visual Studio Code now in the cloud. You've got to be able to look at your environment variables. You'll be able to do live log tailing directly within the Lambda console. That's really helpful. We've been doing work on the local IDE experience. So if you're using Visual Studio Code, the AWS toolkit for Visual Studio Code's serverless section has been boosted up. There's now a new section called Application Builder, and this allows you to build and operate and synchronize and deploy and monitor all your application in one place. You don't actually have to jump out of your IDE to be able to interact with Lambda and build applications. So I suggest you have a look at the new Application Builder. It's within the latest automatically updated part of the AWS toolkit for Visual Studio Code. That's just the beginning. We are looking at adding many more developer experience features. And then, of course, we're going to keep giving you more controls over services. We've had a whole bunch of governance things that have come out over the past year or two, and we're really focusing on that to be able to have the confidence that you can run Lambda and many other serverless services within your organizations. Step functions and Event Bridge last night came out with private API integrations. So if you are connecting using over VPC Lattice or VPC endpoints, just makes it so much simpler. And last week as well, if you're consuming via Kafka, we've got a new provision mode for Kafka. Allows you to pre-provision resources, really be able to process your streaming data really quickly, and also abstracts a whole bunch of the networking stuff out of that. So also great for developer experience. And of course, we're going to be adding more and simpler and broader integrations. Just want to be able to do more things with your serverless services. So in the time today, I did promise and I did say we were going to be covering a lot. Are you all okay? Do you need a breath, a glass of water? We've got some thumbs up in the front, so I appreciate it. So there's obviously, you probably need some time to digest everything, and that's just what we thought. So that's why we, behind the scenes, we started off by looking how behind the scenes, what the serverless evolution was, how a seemingly innocuous little change in Amazon Event Bridge with the latency, brings a whole lot of new application architectures to light. You can get to, async like it's sync. I think that's a sort of powerful construct. Using service integrations, using configuration and running far less code than you actually need to. And then the power of Lambda and the power of Fargate and with all they can do. Lambda and its flexibility and its scaling up mechanism. And ECS and Fargate, easy being able to run containers that can run huge workloads over huge amounts of time. And then taking it to the next level. I love Rand's section, building production-ready serverless applications, which you can then scale out and you can use blueprints and you can create these architectures that you can cookie-cutter approach across your organization and be really efficient to build those serverless applications. But there's still, of course, many other best practices available, so please look at the QR code. We've got links to all the different sections, all information that you can find out how best to build the best serverless applications. And then, of course, you can continue your AWS serverless learning. There's AWS Skills Builder, there are ramp-up guides, and also there are digital badges, which you can earn some cool kudos to prove that you know your serverless knowledge. And of course, one of our favorite sites is serverlessland.com, your best resource for all things serverless on AWS. There are patterns, there are many workshops, there are repositories, there's sample code, whether you're doing Rand's blueprints or CDK code or Terraform code, a huge amount of stuff for building serverless applications, all available on serverlessland.com. And then I just really appreciate, Rand and I really super appreciate you joining us here today. We appreciate you spending time with us in what is a busy reInvent, and hopefully we've been able to give you some cool things to think about. So if you do like deep technical content, we would really appreciate some feedback in the session catalog. This is a 400-level session. Hopefully we've had enough deep dive stuff in there as well. Please let us know. A little slightly bribing tick. If you do a 5 in there as well, then we know we'll come back next year for even more deep technical content. Our contact details here are on the slides, and we'll be around here for a bit and also in the corridor if you have any more questions. But thanks so much for coming. Enjoy the rest of your reInvent.